Hi guys, good morning. So in the last video, we saw about BFS, very standard traversal algorithm. Now we will see the 5 types of problem we actually encounter in a BFS algorithm when we see the problem related to the BFS algorithm. So before moving on to the first problem, I just want to tell that I have compiled a list of BFS algorithm problems. So you can just have this whole list linked down below. I'll just update this list for every algorithm whatsoever I'll teach. The problem list will be entirely this PDF. And what we're gonna see in the next videos is like the first type, which is actually the simple BFS traversal. The second type, which is actually the implicit graph BFS traversal, which means, okay, the matrix is given to you and you have to do a BFS traversal on that matrix. Next, you will see a multi-source BFS where actually rather than starting from one node, you will be starting from multiple nodes. Then we will see the BFS with bit masking. It's a hi-fi way of saying that we can visit one node more than one time. In a BFS, we actually visit a node once, right? But here we can actually visit a node more than once. And the last but not least would be problems in which both a BFS and a DFS is applied. But we will still study all these kind of problem like this one, especially which includes DFS ones after we study DFS. So we will see in the next coming lectures about these 4 standard problems which we actually encountered which are related to BFS. Let's start with the first one, and it is very standard, very basic BFS algorithm problems where just straight it is being applied. But forget for now that you know a BFS is being applied here. I'll just let you know, okay, how it starts, what actually made us think that, okay, now a BFS is being applied here. So just clear your mind, okay, you don't know anything like BFS was going to be applied in this problem. Just make sure of that. I have to tell you because I just wanted to let you know what is upcoming in the next lectures, and also that you have this practice problem set which you can actually practice by your own. So yeah, without further ado, let's start with this problem. So basically, first I have just picked a very easy problem. Find if the path exists in a graph. It is a problem which can be done by either BFS or DFS. Although we have not studied DFS, but in the next lecture, like in the next upcoming lecture, we will study about DFS also, which is depth first search. And after that, you will be able to solve it, but it can be solved by both BFS and DFS, and it's a problem which we actually see when we will actually study DFS. So yeah, I have just let it, but still, as you have understood about BFS in the last video, I'll highly recommend to solve this by your own. But we will see the next problem, which is snakes and ladders. The problem statements is pretty big. I'll just explain you by the example itself. We are just having a matrix as a snakes and ladders game in which you will start from the node 1 and you have a dice in your hand. You will just roll the dice. Whatsoever value will come in your dice, you can just move number of steps ahead, because a dice can have at max 6 values. So I can just get from 1 to 2, which means I can jump 1 step, 2 step, 3 step, 4 step, 5 step, and 6 step, which means from every cell I can reach to next 6 cells. It is how it is done. And as we know that there is a twist in this moving game. What is that? The twist is the ladders and the snakes, which means if I move one step, which means if my dice rolls are 1, so I should have reached 2, but I have a ladder from 2 to 15, so I'll just reach 15 rather than staying at 2. It is the twist in this snakes and ladders game. It's a very famous, very standard, very basic game you must have played. And the same goes that, okay, if anyhow I reach the node, let's say 17, there's no chance I'm gonna stay at that place. The snake will bite me and will reduce my value to what? To actually 13. And here also, if I'm at 14, I will have used the ladder and I'll reach 35. What my task is that, okay, how many minimum number of steps? Let's see. what are the least number of moves required to reach the node n square? I know I'm starting from 1. My operation is to move in one step. I can move these 6 nodes. In the next step, I can move, like in the next step from 5, I can move to the next 6 nodes, which is 6, 7, 8, 9, 10, and so on. So, and how many least number of steps I can actually reach this last node, which is 36. It is a problem, which is what it is saying. Now, if we clearly look at the input itself is saying that, okay, how the matrix will look like. -1 is nothing but, okay, no snakes or no ladders. The value indicates, okay, from this cell right here, this cell, as the cell is 2, we know because it is 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So we know from this cell 2, I can reach the cell 15. It is the cell 17. I know from this cell I can reach cell 13. From here, I know, okay, from this cell, which is cell 14, I can reach cell 35. It is how the input will look like. The matrix will indicate me, okay, if I have some value other than -1, for sure a ladder or a snake would have been there, and the ladder would have whatsoever, ladder or snake would have brought me to that location, which means to 15. If I'm standing at 2. Cool, very cool. Now you got the problem. Now let's recap what the problem wants us. Problem wants us, you start from 1, you have 6 options to go to the next cell, and you have to ultimately reach in the least number of moves to the cell 36. And you have to reach this cell, which is n square. Understand one thing. From 1, you have to reach n square. In what? In least number of steps or the shortest distance. Whensoever something like this comes, okay, I am starting from a cell, I have 6 more options to go, and after that more 6 options, after that more 6 options, and then I want to reach from 1 to the node n square in the least number of steps, and it's kind of a graph which is being made. Something like a shortest distance from 1 to n square, I need to find out, kind of, right? Why not use a graph BFS traversal? Because BFS, as I'm starting from 1 and I have these nodes, which is nodes are 6, and again nodes are 6, again at every level for every node, nodes are going to be 6, 6, 6. Which means that I would love to travel level wise to actually reach to my final node. Not understood? But wait, let us see. We one thing we know, if we roll a dice, we have 6 options. So from one cell, I can reach to next 6 cells. From 1, I can reach to 2, 3, 4, 5, 6, and 7. 1, a gap of 1, 2, 3, 4, 5, and 6. Cool. But we actually also know that, okay, my cell 2 has a ladder to cell 15. So for sure, I'll just not stay at 2. It will actually become a 15. It is when 1 dice, which means the dice is rolled once. It is how my state will look like. When the second time my same dice is being rolled, then I'll just move from what? From 2? No, from 15, because actually I have reached 15. Because of 2. From 15, I have again 6 options to go, which is 16, 17, 18, 19, 20, 21. 16, 17, 18, 19, 20, 21. But still, one thing, no. As it was from node 17, it was actually a node 13. So I will just mark it and I'll just get a 13. Again, if I just go on making, my graph will look something like, from 1 I just moved to all these nodes, from 15, which actually was replaced by 2, was moving from 16, 17, 18, 19, 20. Then from every node I'm just trying the every possible nodes, and ultimately if I have the last node, which is 36, I want to reach from here in the least possible way to here. Let's say if we had some node, some arrow, something like this also, was it required that we actually move from here, sorry, we actually move from, let's say, here, then here, and then again here? No, right? It is always good to actually travel level wise, that okay, because I know my answer would be at this level. So for sure, I want to go at these steps to actually reach my answer. So I just want to find the shortest possible distance from my main source node to actually my main destination node. Understanding? Shortest possible distance, least number of steps from what? From 1 to n square. Here comes the level wise, the breadth wise traversal, which is BFS. Because I will just simply do a BFS traversal, which will actually help me traverse the level wise. Okay, initially I start from here, the distance is 0. Ultimately, I just wanted to find out, right, number of dice rolls or number of distances, number of moves. So I can just say a distance array is equal to a moves array, because ultimately in future problems you will see the shortest distance between node this and node that, the shortest distance from here to here. So BFS is always related to shortest distance from here to here, from here to here. So it is the reason that we just have normalized just saying, rather than moves, I will just write the array as distance, which will actually show me, okay, the distance up till here from here is 0, which means number of moves, because we are starting from 1 itself, right? So number of moves are 0. Then I just, in move 1, which means in distance 1, I just reached at this particular portion. So to reach at 15, 1, 4, 5, 6 and 7, my number of moves required are nothing but 1. Again, if I just go on to do every of these nodes, and also from every of these nodes, like every of its child, I just go on. So again, the distance will be nothing but 1 plus 1, because it's the next. It is 2. Distance will be 2, which means number of moves will be 2. Ultimately, again, I'll just go on to every of this child. It will be 3. Again, I'll just go. Ultimately, it will be 4. So I'll just keep on going ultimately until I find my actually node, which is n square. It is the same thing which I have written. I will just traverse level wise and will just try to find the node n square until I reach that node n square. And as we are traversing level wise, because we want to find the shortest minimum number of moves, shortest distance or minimum number of moves, both are same thing, required, thus we are using a BFS traversal. Now, we for sure know, okay, we are grabbing, we are just moving down the level, we wanted the number of moves, and number of moves we are just grabbing as a distance array, because it's very standard to use a distance array in a BFS traversal. So how it is being updated, it's nothing but, as we saw earlier also, if my distance of parent is so far, let's say something as 4, so distance of child will be nothing but my distance of parent plus 1, because it's just next parent and then child. It's nothing but plus 1. We now know, okay, how my BFS traversal will look like. I'll just start my BFS from node 1. I'll just do a traversal in which I update the child distance plus 1, and as soon as my sums, as we know that a few cells are actually modified, so I'll just, if they're modified, I'll just modify them to actually reach to their actual cells. Basically, if I reach to 2, so rather than putting 2, I'll put a 15. I'll show how, and ultimately I just keep on try to reach the node 36. As soon as I reach it, I'm good. I have found my shortest distance, which means minimum number of moves required. Let's see the code pretty quickly. It's pretty easy. It's nothing but what we did. It's just that how we try to code that same thing. Anyone can code it differently. I'll just highly recommend for you guys to code it actually with yourself. The same code I'm going to show you in C++, but exactly same code is also being pasted in Java also. So you can just grab that PDF out, open that PDF parallelly with this code. It's exactly line by line the same thing. Cool. Let's see. Firstly, we have some variables we initialized. We can just have it anything. Now comes the main part, which is the cells array. This is nothing but it will just grab me. See, what I wanted was for every cell right here, it is a cell 1, right? It is a cell 1. I should know, okay, the cell 1, but the actual cell in a matrix is represented by its row and column. So I'll just say, okay, this cell 1 actually is the cell at the row 5 column 0. So I just need to maintain that thing. Why? Because when we are iterating on this particular whole thing, okay, if I'm moving, because I just know I have to start from 1 and I can reach to 2, 3, 4, 5 and 6 and 7. But the input which is given to me is this boards array. boards array is nothing but a matrix, which means if I am saying, okay, I move from 1 to 2, I should also be knowing from 2 I can reach to 15, and this thing from 2 to 15, it's actually told by my board matrix, which actually gets the input as row and column. So to actually tell for 2 my row and column is this, which is 5 and 1. Now I will just give it the input to my boards array and will just let it know, okay, boards array of 5 comma 1, it will give me 15. So I'll just say, okay, my 2 actually points to 15, which means I just replace my 2 by 15. It's the reason I just needed my number, which means 1 2 3, to actually what cell, row and column it represents. So I'll just grab that thing, which means it's nothing but from array to nothing but a pair, which means this whole thing, one element is actually nothing pointing to a pair, which means row and column. So as I want, I can just grab this. Let's say I want the row and column of, let's say, this whole cell 3, which is the number 3. I can just grab it anytime I want. There's a hack also for the same thing, but it's a very standard hack to actually reach to any of the coordinates of a cell. It is being used in the matrix problems a lot, but I'm not discussing this particular hack right here because I just wanted to explain you the BFS rather than solving this problem super optimally. It will just reduce a space by little bit. It will not reduce the space in O of n terms, but it will just reduce the space in actually like the runtime terms or these space terms. But it's actually a good thing to learn. But I'll not discuss the same thing because it's actually a BFS problem rather than this actual snakes and ladders problem. So what we will just simply do is that, okay, we'll just grab this whole cells. How to update this? It's nothing but it's very simple. I'll just grab my whole row. I'll just start from my last row. I just have this variable as, okay, 1, because as I'm moving in the row, last row, I need to move column wise, which means from column 0 to column 5, I'm just moving 1, 2, 3, 4, 5, 6. Now as see, it is being increased, LBL, which is being increased every time. So I'm just updating my cells every time and I'm just updating with the row and column. But how we are moving in this particular loop is nothing but I start from the last row, moving from left to right, and then I'm just moving from right to left. I just reverses my column. Column is nothing but I just initialize my column by actually 0, 1, 2, 3 up till n-1, and every time I'm just reversing that because I'm moving from left to right, right to left, left to right, right to left, like this. Thus, okay, my cells array is ready and I am good to actually start working on my BFS traversal. How? As standard as that, we will have this distance array, which will actually help me update the distance, which means the number of moves as we go. It is minimum number of moves. Standard BFS traversal, grab, we have a queue have the input first root node. I just have a loop while my queue is not empty. I just grab the top front of that queue. I just remove that from queue. It is very standard BFS traversal. We also saw in the standard BFS traversal video. Then after that, the main part comes. As we have the node, we then go to its child. I just go on to its child. The child are nothing but for every node, the number of child possible are 6. Why I'm saying not exactly 6? It's because for the nodes which are actually, let's say, 33, the number of child possible can be 34, 35 and 36. Not more than that, right? So it's the reason we have put, okay, a limit of n square also, that the child can't go beyond that n square. Now, I know, okay, my child is, let's say, if I am the x, then my childs can be x plus 1, x plus 2, x plus 3, x plus 4, x plus 5, x plus 6, provided it is under n square. But as I said, if I grab that child, okay, my child is 2, but I also need to make sure if it is moving on to some other value, which means if my child was 2, it was moving on to 15. So I need to also grab that, right? just grab the same thing out. I'll just grab, okay, what is the row and column of my next is nothing but my child. Okay, next is up, it's my child. What is its row and column? Its row and column, I just got that row and column. I just check, okay, if that row and column is not equal to -1, which means a value was there, I just grab that value and it is my actual destination value. Else whatsoever value would have been there, which means if it would have been 3, it would have been 3. If it would have been 4, it would have been 4. But if it would have been 2, so it would have returned a 15, and that would be my new destination value. Then I will just check, okay, if that destination, if that whole destination distance is not equal to -1, which means, okay, it's not is equal to -1, so it is not visited so far, because if it would have been visited, it would have got that distance value because it's initialized with -1. So if it is -1, which means it has not been touched so far, I will touch it for the first time. I will visit it for the first time. I'll just grab and I just mark that distance of that particular node as right now, because it will be the minimum distance as I'm traversing level wise. So it's the first time I'm just grabbing that particular node. So I just update that distance right now. If it is -1, it is not visited. I just visit it by just saying, okay, the distance of this destination is nothing but my parent distance plus 1. As I showed you here also, how we just are updating our distance, parent plus 1. Cool. And then I'll just say, okay, how a BFS works. You just grab the child, you just now put the child in my BFS queue. Ultimately, I just need to return the distance of my what? Of my node n square, because ultimately I am starting from 1. I am about to reach my node n square. I have to reach my node n square, and I just say, okay, what is the distance to actually reach my node n square? And I'll just reach that node. And the time complexity is nothing but O of n square, as I'm actually moving on to every cell of this array exactly once, because once a cell is visited, it's pushed in queue and will not be pushed again in my queue. As I am saying, okay, I'm pushing my cell only when its distance is -1, and as soon as its distance becomes something else, it will not be pushed in my queue, which means my distance thing is actually working as a visited thing for me also. Cool. Then I'm just iterating on every of these values. Thus my time complexity is nothing but O of n square. Space is also O of n square, primarily because we are using a distance array which is actually storing the distance of every node, which means it's 0, 1, 1, 1, 1, and so on. So it's grabbing the distance of every node. Although this question, we actually also use this cells array to actually store from 1, like value 1 its row and column, value 2 its row and column. But I'm saying, okay, it was not required at all. You can just simply do by this particular method right here, and just avoid using that cells array entirely. And thus but still, if you also avoid that same thing, but still the space complexity will be still O of n square. It's just that, okay, it will be reduced a bit. And the same code for C++ and Java is below in both screenshot format and also the code format. I hope that you guys liked it. If yes, then do the like button. In the next video, we're going to see the next variation of our problem of BFS, which is nothing but BFS on a matrix, which means implicit graph. It was also a matrix. But actually, we actually tried to do the same thing. We actually made a graph out of it, right? But the next thing would not happen. It would that, okay, every cell will actually work as a node itself, and we are moving actually to other cells by just moving a graph. You can also count it as an implicit problem or not, but it's actually a very basic standard BFS problem which we discussed right here. I hope that you guys liked it. If yes, then do the like button, and see you again in the next video. Goodbye, take care.